Hi all. Good morning, good afternoon, and good evening. So welcome to the OWAS Kerala chapter mid July 2020. We are starting the event in another 5 minutes. Thank you. Hello everyone. Wherever you are, hope you are staying safe. Myself Adarsh Nair, co-leader of OWAS Kerala. I welcome you all to the OWAS Kerala chapter meet July 2020. Today, we all are here in this online platform for a technical webinar conducted as part of the chapter meet. Because of the current pandemic challenge, this time we are conducting this chapter meet virtually in association with HACKAP. HackAP is an international virtual hackathon organized by Kerala Police to build smarter solutions for the uh, betterment of future policing. Let's have a look into more details on Hack KP. So welcome back. If you are interested in participating HackKP, or if you want to contribute something back to the society, please do submit your nominations via the official website hackap.kerala.gov.in on or before 26 July 2020 midnight. Today, we will have a session on buffer overflow, which is highly critical in terms of application security. We have Shibin, Shine, and Anil as our speakers, who are also security engineers at UST Global. They have a very good experience in the cybersecurity domain. Hope you find this session useful and with some solid takeaways. If you have any queries or you need more clarifications in between, please drop comments in our Facebook and YouTube channels. The orators would definitely be addressing your queries. On behalf of OWASP Kerala and HackKP, I welcome Shibin, Shine, and Anil to take the session. Over to you guys. The platform is yours. Thank you.
Thank you, Adarsh. Thank you for the welcome. Uh, Good afternoon, everyone. Welcome to our session, Buffer-overflow. Um, okay, is my screen visible? Anil?
Yes, Shibin, it's visible.
Okay. So yeah, welcome again. With this, today's our topic is Buffer-overflow for Noobs, and we intend to uh, clarify many doubts or many vague ideas regarding buffer overflow. And those who are not aware of what buffer overflow is, we'll be giving you an overview about that also. And talking about ourselves, I am Shibin B. Shaji. I'm a security engineer at UST Global. I'm a cybersecurity enthusiast and a full stack developer. Um, and with me, I have Mohammed Shine and Anil Tom. Over to you, Shine. Introduce.
Thank you, Shibin. Hi all. Hope everyone is doing well. My name is Mohammed Shain. I'm a security engineer at USC Global. Apart from my job, I'm a free-time bug bounty hunter, a CTF player, and a tech enthusiast. I'm also an automotive photographer. I'm one of the core member of the cybersecurity team, DEFCON Toronto. That's all about me. You can take it, Anil.
Thank you, Shane. Myself, Anil Tom, currently working as a security engineer at UST Global Toronto. I'm also a free-time bug bounty hunter and got listed on more than 70 plus Hall of Fame for different companies like Google, Microsoft, Yahoo, etc. And I'm a core team member at Yet Another Security. That's it. Thank you.
Okay, thank you for the introduction. Now, moving on. This is what we will be covering today. First, we will be giving you an introduction to buffer overflow for um, those of you who are new, and that will be taken care of by Anil Tom. And then we'll be looking into a small introduction of assembly language, and we'll be analyzing the flow of an assembly language using GDB. GDB is GNU debugger. So we'll be analyzing uh, assembly language with that. It is a crucial part of our demo. So it is important that you have some knowledge about this. That's why we are introducing this topic today as well. And then finally, we'll be showing you how you can exploit a stack-based buffer overflow. We'll be analyzing the a C program, vulnerable C program with GDB, and we will show you how you can exploit it. Now, handing over to you, Anil. You can take over.
Okay, thank you, Shibin. Today, I would like to talk about Buffer-overflow, how it works, and how it's going, how we can identify, how we can prevent these attacks and all things. Before going to start, I would like to show one comic pic. In this pic, you can see it's a famous comic for the Buffer-overflow. In this, first they asked to type some characters, then he typed, and later he got the Buffer-overflow like that. So let's move to the session. So before going to start about Buffer-overflow, I would like to talk about buffer. What is buffer? In computer science, a data buffer is a region of physical memory storage used to temporarily store data while it is being moved from one place to another. The buffers are typically live in RAM memory, the random access memory. The resource pool divides the process memory into pools. Each pool contains numbers of memory blocks of equal size. These memory blocks are normally called buffers. Buffers Buffers are designed to contain specific amount of data. Unless the program utilizes the buffer has built-in instruction to discard the data when too much is sent to the buffer. The program will override the memory in addition to buffer, because sometimes when the user enter more than what we specified in program, the buffer will automatically adjust and write to another buffer. So when more data get placed by a program or system process, the extra data overflows. It causes the sum of the data to leak out into another buffers, which can corrupt or overwrite whatever data they have holding. So now you guys see what is buffer. So now let's move to buffer overflow. A buffer overflow condition exists when a program attempts to put more data in a buffer than it can hold, or when a program attempts to put data in a memory area past a buffer. In this case, a buffer is a sequential section of memory allocated to contain anything from a character string to an array of integer. Writing outside the bounds of blocks of allocated memory can corrupt the data, crash the program, or cause the execution of malicious code. For example, in a buffer for login credentials may be designed except the username and password of input of 8 bytes. Normally, we have a user and password form will be there, but the intended amount of memory is allocated to 8 bytes. When a user what if a user tries to enter more than that bytes? Like in this case, you can see that there is the actual buffer size is 8, but the user enters in 10 bytes. So the last two bytes will be carried to another buffers. Like that, the buffer overflow works. So now you guys see what is buffer and buffer overflow. So what are the types of buffer overflow vulnerabilities? There are two types of buffer overflow is there. One is stack based buffer overflow. Another one is heap based buffer overflow. So let's start with stack based buffer overflow. In this session, we are more concentrating on stack based buffer overflow. The stack based buffer overflow are more common among hackers. Exploit application and programs by using what is known as stack. Now, what is stack? Stack is the memory space used by the operating system primarily to store local variables and the function return address. The data on stack is stored and retrieved by a organized fashion, like first in, first out, like that. The stack is allocation managed by an operating system, and the access to the stack is fast. That's the stack. Now we move to heap overflow, heap based buffer overflow. So heap based buffer overflow are difficult to execute, and this is the least common common buffer overflow which in these two. Attack an application by flooding the memory space reserved for a program. That's how the heap based buffer overflow works. The issue applies to the heap, which is the memory space used to store dynamic data. The amount of memory that needs to be reserved is decided at the runtime. So, and it is managed by the program, not the operating system. Access to the heap is slower, but space in the heap is only limited to the size of the virtual memory. So now you see what is buffer and buffer overflow and what are the types of buffer overflow. So now let's see some of the famous buffer overflow vulnerabilities that are headlines in our newspapers. So first we see Microsoft CV 2018-8392. So which is affected to Microsoft. The buffer overflow vulnerability exists on Microsoft JET database engine that could allow remote code execution on an affected system. An attacker who successfully exploit this vulnerability could take control of the affected system. An attacker could install the programs, view or edit or delete the data of the data in the system. And if the attacker can create new user with full privilege like admin user, like that, users who are configured to have fewer user rights on the system could be less impacted than the administrator user. To exploit the vulnerability, a user must open specially crafted Excel file. The attacker should send by email or some other way. He have to send the Excel file to the specially crafted Excel file to the victim, and the user should be open it, so that the attacker should do some like social engineering methods to the user to click on and open the file. So that's how that CV 2018-8392 works. So the next one is CV 2019-8745. It is affected the macOS Cortana version 10.15 before. A buffer overflow was addressed with impressive bounds checking. This issue was fixed in macOS Cortana 10.15, tvOS 13, iTunes for Windows 12.10.1, iCloud for Windows 10.7. 7. Processing a malicious crafted text file may lead to arbitrary code execution. UI Foundation is a part of UIKit, the graphical interface framework that provides necessary framework for iOS and tvOS apps, so that it is core of that operating system. So the bug is a critical one. So the next one is CV 2019-3568. It is one of the famous about the WhatsApp. it was when attacker just call one user by even if it is a missed call, the attacker can do the buffer overflow. The WhatsApp suffers from buffer overflow weakness, and attacker can leverage it to run malicious code on the device. Data packets can be manipulated during the start of a voice call, leading to the overflow being triggered, and attacker could commanding the application. The attacker can deploy the surveillance tools to the device to use agent the tag against the target. So now you see some of the famous buffer overflow vulnerability. Now we can check how we can prevent buffer overflow vulnerability. There are mainly three methods to prevent the buffer overflow. So first one is address space randomization. Next one is data execution and prevention. Third one is structured exception handler override protection. So let's see with the address space randomization. The address space randomization randomly moves around the address space, the location of data region. Like uh, when we typically normally do the buffer overflow attack, the attacker should know the exact location where the uh, buffer going to execute, or where the code going to execute until now. So but if what if the the software what is the program randomly changes the location every time? Like that, we can prevent the buffer overflow by randomizing the address space. Makes it virtually impossible to do the buffer overflow. The next one is data execution and prevention. It flags certain area of memory as non-executable and executable, like which stop the attackers to running code from the non-executable region, like bin bash or somewhere. We can prevent like that. The next one is structured exception handler override protection. It helps to stop malicious code from attacking. Structured exception handling, a built-in system for managing hardware and software expectation. It thus prevents the attacker from being able to make use of structured exception handling override exploitation technique. A functional level and structured exception handling override is achieved by using stack-based buffer overflow to overwrite an exception register record stored on a thread stack. In this session, we will cover more about 32-bit stack-based buffer overflow, and we will show some basic code in C and how it vulnerable for buffer overflow. And also, we will show a application buffer overflow in Linux 32-bit. And it will covered by the Shibin in coming session. And now I would like to pass Shine to explain about assembly language, basics of assembly language.
Thank you, Anil. Yeah, it was a good presentation. Before moving to my session, we got a question. The question was, which language handles the memory allocation securely? Okay, I know that C++ actually handles the memory allocation securely. Do you have any other answers or any suggestions, Shibin?
C++ handles security, but if they are not coded properly, they might lead to some attacks. Like if you are doing some, say, if you are using the function rand in C++. So if you are not performing any checks, an attacker might be able to guess the randomized function, because nothing is truly random. That no number is truly random. That is generated by the C++ code. So it basically depends on how you code the entire program.
Thank you, Shibin.
I hope it clears the doubt.
Okay, Shibin. Okay, now let's move to my topic. My topic is Introduction to Assembly Language in x86. Okay, before moving to my session, I could say some things. Like my session is not a complete one-on-one session about assembly language, because assembly language is a vast topic, and I have scratched some part from assembly language and put it in my presentation to get an overview about assembly language and how to use it in our like you can use my presentation to get more idea in the lab, which is demonstrated by Shibin. Okay. Before moving to assembly language, I should also say that what is the importance of assembly language in buffer overflow? That is, understanding registers is very important to understand how a program works, or to get the idea of the program. Also, understanding instruction sets can be used for exploit development. So this is the key concept of assembly language in buffer overflow. So let's move to my topic. Okay. What I hope to cover today is the fundamentals such as registers and instructions. And Shibin will be showing a practicals in that. Also, the tool GDB, GNU Debugger, which is used to analyze the program flow. Okay. So let's read what an assembly language is. In computer programming, assembly language or assembler language, which is often abbreviated ASM, is a low-level programming language in which there is a very strong correspondence between the instructions in the language and the architecture's machine code instructions. I got that. You guys might be confused while reading that. This is what I got from Wikipedia, and I will break it down and say it in my own words. Okay. Actually, an assembly language is a language that can be used directly to tell computer what to do. So that means we are instructing the computer what to do next. So this can be done using assembly language. And actually, assembly language is human readable. So it's better than understanding the machine language, which is binary. So this is the meaning, or this is the definition of assembly language. So that's it. This is assembly language. I hope you got an understanding about assembly language. Now, registers. I will go deeper into registers in the coming session. Before that, I will give a brief idea about what a register is. Consider a school or college where they use a register as a book where the teachers stores the data of students, teachers, attendance, timesheets, etc. So basically, register is used for data storage. So in computer, in CPU, a register temporarily holds frequently used data and instructions. So we could also say that it is a temporary storage for storing instructions and memory addresses. This is what a register is. Now let's move deeper into registers and what are the types of registers and what are inside the registers. We could get that. Okay. So I think you can see that image which is in the right side. Okay. So this is the structure of a register. There are 6 general purpose registers, and these are EAX, EPX, ECX, EDX, ESI, and EDI. These are the general purpose registers. And out of this, the first 4, which is EAX, EBX, ECX, and EDX, are basically used for arithmetic operations and data movement. And we will be covering this in our session, in the practicals as well. So understanding EAX, EBX, ECX, and EDX is important. Apart from that, we will be also covering another register that I will convey in the next slide. So this is the structure of a register. So we could understand that a register is something which can be addressed in 32 bits, and it's broken into 2 parts, which is 16 bits each. Also, this EAX, EBX, and ECX and EDX have 2 subregisters, in which one have 16 bits and other subregister is divided into another subregister which have 8 bits each. That's AH, AL, BH, BL. That's A high and A low. That's it. So let's talk about the primary 4 registers, which is EAX, EBX, ECX, EDX. Okay, As I already mentioned, they have 16 bits and other two 8-bit 16, which equals 16 bits registers, sub-registers. Okay, AX. This can be used as general in EAX, EBX. So AX, I'm focusing on the term AX. AX is the primary accumulator. It is used in input and output and most arithmetic instructions. For example, in multiplication operation, one operand is stored in EAX, in AL or AH. That's it. Why we are storing in AH and AL? I will give a basic idea. Because consider the value is more than 8 bits. If the value is more than 8 bits, the whole register is used. And if the value is less than 8 bits, this AL or AH is used. This is the purpose of AL and AH. So the next one is BX, which is also known as base register. It could be used in indexed addressing. And CX is known as count register. And CX register store the loop count in iterative operations. Then DX is known as the data register. So these are the main registers which we are going to which we use in our practicals. So then the next one is the next register which I missed in my presentation is EIP. EIP or extended instruction pointer. Extended instruction pointer. It always points to the next instructions to be executed. So it stores the value of the next instruction. You just understand in that way, so we will not get confused. So this is what we should understand about general purpose registers. So this is not, as I already mentioned, this is just a basic idea of assembly language and registers and all other things. So you can contact me if you need more resources or more idea about assembly language, or if you want to start with assembly language. So I have only mentioned what all things which are needed in our session. So this is not about complete bootcamp about assembly language. Now we can move to a simple assembly code in the next section. So can move to the next presentation sheet. Okay. Okay. Now we'll move. We'll go to instructions. So basically, it's very not difficult to explain what an instruction is. It's the same meaning as the word seems. Example, MOV or move. Move is used to move the value of one value to a register. Understand in that way. I will explain with an example. Example, move EAX, 8. The integer 8, the value of integer 8 is moved to EAX register. That's what happening here. Always remember, the values are transferred from the right side to the left side. So in the first instruction, the value 8, the integer 8 is moved from its place to EAX. So now the value of EAX is 8. This is the basic concept of move instruction. Also, this is an integer. We could also specify an hex value, which is identified as 0x enter at the start. So next one is okay. Sorry, the presentation closed. Okay, the next one is move EBX, EAX. Now we know that the value of EAX is 8. So I'm again going to explain with the value 8. Now the value of EAX is 8. Now the value is moved from EAX to EBX. So then EBX value is replaced with 8 right now. As I already mentioned, the right value always move from right to left. So then the third instruction is move ECX, EBX. This is used to move the address of EBX to ECX. Okay. Now, another instructions are add, subtract, increment, and decrement. As the name suggests, these are used in arithmetic operations. So the first instruction is add EAX, 2. Consider the value of EAX is 8, and we gave it as add EAX, 8. It's straightforward. Now the value of EAX is 10, 8 plus 2. Now consider the same example in the second instruction. Subtract the value of subtract 2 from the value of EBX, which is 8. So now the value of EBX is 6. Increment and decrement. These are used for incrementing the value 1 and decrementing. Example, now the value of EBX is 8. No, 6. From the before question, it's 6. So I will explain with that answer. So INC or increment EBX will give the value as 7. Then EAX, the value of EAX is 8, and decrement EAX gives the value as 7 as well. So this is the basic instructions which we need to understand in our session. And I'll be also giving some hints and some things to Google in the next slides. So you can explore more about instructions in assembly level language. Okay. XOR. Bitwise XOR of each value. This is also straightforward. Like we have the value of EAX in binary as 1011 and EBX as 0101. In XOR bitwise operations, the same value, that is 1, 1, will give the answer as 0, and the different values, which is 0 and 1, gives us 1. So from that example, you could understand that what XOR does. Now, push and pop. If you are from a computer science background, you might know what is push and what is pop. But don't worry, I will tell what is a push and what is pop. Push EAX. This pushes the value of EAX into the stack, and it is going to it will be in the top of the stack. And pop is used to fetch the value from the top of the stack to EBX. So basically, push is used to give the data, and pop is used to take the data. Then CMB. CMB is used for comparison. I will explain it with a real life example. Consider an application where we need to use a key or a subscription key to purchase or to unlock that application. So this is the value. There will be two values, EAX and EBX, two registers and two values each. Consider the value which is given by the developer is stored in EAX, and the value which is given by the user or us is stored in EBX. The CMP will compare and check whether those are equal. And if it is not equal, it can. If it's not equal, it can send it to the exit function. This is how comparison works. Okay, nope. Nope is nothing. It doesn't do nothing, and it's no operation, as the name suggests. It's nope. Okay, now I will explain a simple structure of an assembly code. So as I already mentioned, assembly level code is easier or human readable. So, okay, the global start. This is the directive global tells the linker that the entry point of a program is start. So I will also explain what is linker in the comment session. Sorry for not including what linker in the like before. So I will explain it. First, we will tell the linker that the start is our entry point. Then start is the start of the program, and like before, I already mentioned, like the value moves from right to left. Now the value of EAX is 8. Right? Move EAX, 8, you can see that, and the value will be stored in EAX. And move EBX, EAX. Now the value of EAX is 8, and now the value is shifted to EBX, and now the value of EBX is 8. So this is how we write a simple assembly code. And in the demonstration, Shibin will be showing how these things works, and how each register store and each register shift the data. Okay, now GDP. Okay, GDP is nothing. It's a tool which is used to analyze the program. It's GNU or GNU debugger. We all know what a debugger is. A debugger is a software which is used to analyze the program flow, or which is used to find the bugs or the errors in a program. So GNU debugger is used in our session to analyze the program or the assembly language, and we are also using this GDB for the exploitation purpose, or finding the pointer, or finding the the buffer which can be exploited. We also there's a small change in the GDB which we use. It is we are using uh, a special version of GDB in which a special version of GDB which is known as Jeff, which can be used for it is user friendly, or it has a good interface. So
Makes it more readable.
Yeah, it makes thank you, Shibin. It makes us more readable, human readable, so we can understand the registers, the pointers, everything in an easier manner. So all these steps will be covered by Shibin in the demonstration. All to you, Shibin.
Thank you, Shane. That was a wonderful part. Okay, so I'll be showing you a demo. Can you see my screen? A terminal.
Yes, Shibin, it's visible.
Okay, so first we'll be writing an assembly language, and then we will analyze the program flow using GDB. So I will open a file called demo.nasm. Yes, this is it. So first we will be writing global, and this says that the entry point of the program is start. And now we will go down, and then we will enter start, and then we will write our assembly code from here. So for the sake of demonstration, let's do some arbitrary values like move EAX 8, and then move EBX, EAX, and then we will add value of 2 to EAX, and then we will subtract EBX. We will subtract 2 from EBX, and now we will include a knob, and then we will include an increment of EAX, and then a decrement of EBX. Okay. So now I have saved the program, and now we have to first assemble the program. So to assemble the program, Linux has an inbuilt tool called nasm, and we will pass this file demo.nasm, and I'm running on a 64-bit Linux, but this program is 32-bit, so to run it in 32-bit I'll have to give this argument so that it will compile it according and it will make it compatible with 64-bit. And -o, let's say demo.o. Okay, that has now assembled. Now let's link it. Link -m minus.
Shibin, can you zoom the screen?
Okay. Is this okay?
Yeah, okay.
Okay. 386 and -o will be demo, and the file that we are gonna give it is demo.o. I guess that has linked, and we have a file called demo. Now we will use GDB to open that file gdb./demo, and it has loaded in GDB. If anyone has used normal GDB, you can spot the difference easily because there are some color codings here. See, that's the specialty of Jeff, using Jeff with GDB. It's an extension that is available. It's in GitHub, so it makes it more readable. Like I will show you. So in GDB, so to analyze a program, we'll have to set breakpoints at different points. Like breakpoint is when you have to stop or pause the execution of a program. So if you recall, we had something called start. So we'll put a breakpoint at start. So to put a breakpoint, we type break start. Or to make it more simpler, we can just type the start. And you can see it has set a breakpoint at start. And now we can run the program. So to run the program, we can type run or just R. So you can see these are all the registers, and this is the stack, and this is the code. For now, we are just interested only in these three parts only. So okay, so now as Shine told, EAP always points to the next address to be executed. So the next address is 0x0804860. So if we go to the code, we can see that this is that address, and if we continue the execution, this will be executed, and the value of EAX, which is currently 0, will be updated to 8. Now let's see. Now to continue the program, we type C, or if you want to just do a single step, we type SI. And a single instruction was executed. And you can see that the value of EAX is now 8. And see, it has highlighted the register in which the recent change has occurred. That's the advantage of Jeff. And now if I continue using SI, because I want to continue the execution step by step. So I will type SI, but instead of typing on SI, which is more redundant, I will just hit enter. And what it does is it will execute the previous command that I entered. Now in this stage, SI was the previous command that I entered. So if I press enter, SI will be executed again. Now command was EBX, move EBX, EAX, which means the value of EAX will be moved to EBX. As you can see, the value of EBX is now 8. And now, if I continue the execution, now the value of to the value of EAX, I added 2. So it now becomes 0xA. A is a hex for the decimal 10. So we can confirm that it worked. And now we will subtract EBX from, no, we will subtract 2 from EBX. So when we press enter, yeah, that has taken place, and the register EBX has changed. Now we have picked a knob. So if we press enter, nothing changes. That's the functionality of knob. It does no operation. Now the next is increment EAX. So now the value of EAX is 0xA. So now if I execute that command, it is now 0xB. And then now the decrement, the value of EBX was 6, and now it is 5. So that's how you analyze a program with JDB. This was done to make you comfortable with all this, like the stack and the registers and the code. I hope this is clear. Now I will be exiting this. Okay. So, so finally we have reached our most important part of this session, which is stack-based buffer overflow. And now this is a vulnerable C program which we will be concentrating on today. As you can see, it has a one function and it has a main function, and that one function is defined below. So those of you are not comfortable with C, the execution starts at C. So when the program starts execution, it will directly jump to main, and then the execution continues. So inside main, if any other function is called, that control will be given over to that function, and it will execute, and then it will return back after completing the execution. So here we are really interested about this. Like, we have defined a character array called buffer, and it is of length 256. And then we are using an strcpy, which is string copy. So what it does is it takes a value input, and then it will copy it to the buffer. So this is an example of a worst coding practice, because uh, no checks are being implemented to see if the size of input is less than 256 or not. It just takes the value input and then blindly writes it into buffer. So okay, I will splitting my screen. Is my screen and terminal both visible?
Yes, Shibin.
Yes, Shibin.
Okay, so first, according to that program, I will show you the program again. So this is the program. So if it is working as intended, there will be a memory allocated for the 256 characters that is here. And if the input is less than 256, it will stay within this memory buffer. So now what happens if we try to enter more than what is capable? So we will write a small script file for that. Let's call it demo exploit. Okay, we have started. Now we will write, this is a Python file. Now we will write like character A, like let's make it 300. We will type 300 A's, and then we will print that value. We will save it. Now we will see what it generates. It will print 300 A's. Now we will write this output into a file, demo1. So I use this to write it into a file. This is a basic Linux command. So okay. So if I see, I can yeah. it is written onto the file. Now we will try to enter it, like pass it into our vulnerable program. I have already compiled that program beforehand because there was a chance that if we try to compile it now, it might lead to some errors. So I compiled it beforehand, and it is called vulnerable. And now I pass argument as cat demo. As you can see, we managed to crash the program, which means we wrote more than what was capable for the buffer to store. So we managed to crash the program. So let us look at that in GDB. Okay, we loaded the program on GDB. So now we will first set a breakpoint in main. This is a C program, so it has a main function. So we will set a breakpoint in main, and then we will run the command using R, and then we will pass the parameter like the input is demo1, and then we will enter. Okay, as you can see, we have entered. So now um, let's see what all functions are available inside the main function. So for that I use disassemble main or this as main. So if I am an attacker and I don't know the source code, I can just take that file and disassemble the main function. I will get the assembly level equivalent of all the function. And it is more user friendly because if you remember, we defined a function called one function and it is showing up here. So we copied that, and now let's disassemble and see what that function holds. Okay, so this is that function, and it is calling us strcpy. So anywhere there's an strcpy, it might be vulnerable if there is no checks implemented. So okay, so let's copy this address. Okay, since this is another function from main, like while executing a function, the control will be transferred to this one function, and then after the completion, it has to return to the main function, right? So in order for the function to tell the main program that it has completed the execution, there's a instruction called ret. It tells that the function execution is over and can return to the normal execution. So we will set a breakpoint at this point. So for entering a breakpoint, we will copy that address, and then we will hit B. And since this is an address, we will put a star and then paste the address. And now we have breakpoint at this point. And now for us to continue this program, we type C. So you can see we are at the function of ret of the one function. So now if I the EIP currently notice this EIP currently stores this value, which is ret. So if I do a single step instruction, EIP currently holds A, which is which might be one, yeah, which is surely one of the A's that we entered. So we need to find out of those 300 A's, which which 4 A's went inside the EIP. So what we can do is there's a site. Can you see this?
Yes.
Okay, to generate, this site generates like random patterns. So we need some 300 random patterns, and then we will copy this, and then we will create an exploit with that. So we have a file, so we will just copy that, copy it, exploit.py. Sorry, demo exploit, or let's keep it short so it makes easier. Demo2.py. Now let's open demo2.py. So as you can see, this is the earlier value. Now I will just replace that with the string that we copied just now, and that is printed here. Okay. Now I will run that. And then I will concatenate the output. I will type the output to demo2. So if I cat demo2, cat is a tool to print the contents of the file. So if I cat demo2, we can see a list of, you can see a bunch of random characters. So we will be loading this as a payload to our vulnerable file. So say gdb dot slash vulnerable, and then we will do it all over again. Like we'll first breakpoint at main, and then we will run the program, and we will pass demo2 as the argument. Now we will disassemble the one from. We will take this address. Clear works with this. Clear, there's no clear. Okay, anyway, I will continue with this messy screen. Okay, so I have copied that address, and now I will put a breakpoint at that address. Okay, now I will continue the execution. So as you can see, our random string has entered the program, and it is inside the stack also. So if we continue this program, the random value will go to EIP. So if we do a single step execution, we can see that the value I9AJ is inside EIP. So we were able to control what goes on into EIP. So we need to find out at what position I9AJ is located. So we will copy that. Now we will exit. Let's see. It's harder to count in this, so we will go back to that site again, and then we will enter that. So we got the offset, that is 268. So after 268 A's, the next 4 characters will be pushed on to EIP. So let's see if that works. So we will copy that, or just type it, demo2.py to demo. 3.py, and then we will open it. We will comment this out. Okay, so first we'll be entering junk value. We will enter 268 A's, and then we will declare a variable called EAP, and it will have VVVB. Now just after this, let's call it chunk 2, and let's maybe make some 40 C's. And we'll have to print junk plus EAP plus chunk 2. Now we will save that, and we will execute. And let's see. Okay, so we have 268 A's and 4 B's, followed by 40 C's. Yes, 20. I forgot. So we will write that into a file demo3, and then again we will be loading GDB, and again we will set a breakpoint at main. We will run the program. We will cat demo3, and we will plus. Okay, hope it works. Okay, now we will disassemble the one. I will copy this address. Notice that this address remains the same. That is because we have disabled ASLR. As Anil told, ASLR is a prevention mechanism for buffer overflow. So it is by default turned on for all Linux machines, but for the sake of this demo, I have turned it off. Okay, so I have to set a breakpoint at this address. Now I will continue the program. Okay, so if I do a single step increment, yeah, as we guessed, the B is inside EAP. So we were able to control what the EAP can hold. Like we were able to pinpoint the position of the data that we need to modify, so that the EAP can hold the value as it is. So, we found out the offset, and then we tried to enter D, and then now if you look after this 256 characters, we have some unused space. So what we'll be doing with this unused space is we will be entering our malicious code inside this, and we will try to figure out a way so that we can jump our execution from EAP to that shell code. Okay, so this is our next plan. So we will fill some of this unused space with NOP. NOP, as I already demonstrated, it is a non operation, and it will just slide over to the next instruction. So we will chain with a multiple NOPs, and then we will use the shell code here. Shell code is an instruction that is injected by a program. It is powerful because it does direct manipulation of the registers. Like in other high-level languages, you do not have complete access to the registers, but with the help of shellcode, you can directly manipulate the registers. So yeah, sorry. We'll be doing coding that. Demo 3, right? So for the next exploit, I have already prepared this because I took this off of internet, and yeah, that's it. So there are many shell codes that are available on the internet, or you can use a tool called MSF Venom. So MSF Venom is a payload generator that generates when reverse shell or some keyloggers or any malicious code or malicious APK files, malicious Excel files, malicious Word files. Almost everything is there. So you can generate a shell code using this MSF. Okay, so I will just remove that, and then okay, I got a shell code from the internet, and then I filled it with 60 knobs, and then I gave a padding because imagine that the shell code is up to fills only half of the space, so we don't know the exact length of the shell code, so we need to fill the other half so that we will have a control over this space. So what we can do is we will take 268 and then reduce 60, that is the number of knobs, and then we will also reduce the length of the shell code. So it will give the number of A's to be filled so that it reaches EAP. And then let's keep EAP as B to see if this execute very well. Okay, junk is 30, and then okay, then I will concatenate all this, and knob plus shellcode plus padding and EAP and junk. So if everything works properly, we will be able to enter B into the EAP register. So right there. We will enter to demo 4. Let's clear the screen. Now we will see the contents of demo 4. As you can see, there's a unreadable characters and some A's and some B's. And you can see this is a bin. Try to execute some program. So let's see what happens inside GDB. So we will fire up GDB and load the vulnerable program. Now we will put a breakpoint at main, and we will run and pass the parameters as demo 4. And now we will disassemble the one function. We will take this address, and then we will put a breakpoint. Okay. We put a breakpoint. Now we will hit C to continue the program. So, okay. I actually pressed an enter. So, yeah, we injected a shell code, and we were still able to manipulate the data of EIP. Like we were able to control what goes into EIP. So yeah, even after injecting the shellcode, we were able to do that. So next, what we can do is we can point an address of one of the knobs. Like I will show you. This command shows the stack. Okay, just like so. 0x90 is the knob. So we have knobs up till here, and then hopefully this is our shellcode from here. So what we can do is we can point an address which contains a knob, and for example, if I take this address and give it to EIP, the execution will jump to EIP, and then since it is a knob, it will just pass on the execution, and it will go like this, and it will skip this again, and then no execution will take place, but it will be moving forward, and it will eventually hit the shellcode. So let's take this address. I have copied it, and then next quit, clear the screen. I have prepared that exploit as well. Yeah. I used this to see if this works. So doesn't matter. Just clear that off. So now I will enter EIP equal to. Now here we will enter the value of the address. So before entering the value, I would like to tell how you should enter. This is a 32-bit Intel architecture, so it follows Little Indian format. So in Little Indian, you will have to enter it from the back, like in reverse order. So I will show you. It will be much more clear. /x, we will enter C4, and then we will enter /x D3, and then /x FF, and then again /x FF. So if this works, it's well and good. Right then, exploit 5.5, and we will write it to demo 5. Okay. Oh, it's all gone. Okay. Yeah. Now we will fire up GDB and load our vulnerable program. Okay, so we will set the breakpoint at main. Then we will run using our command cat demo 5. Hopefully it will work. Okay, we have it our first breakpoint, and now we will see disassemble the one func. We will copy this address. and then we will set a breakpoint, and now we will hit C. So yeah, it is at the return instruction of the one function. So if I do a single step instruction, you can see that this points to the next address that is going to be executed, which is our knob, the number of knobs. So this is the multiple knobs. So yeah, we can we will do a single step instruction, and it has hit one of our knobs. So we can do a single step, continue on like that, and eventually we might hit a shellcode. It's going on, and we have come to an end of our knob. Now I will just press C to continue, and as you can see, the program tried to execute a new program, which is /bin/dash. It is a lightweight terminal. So yeah, this program tried to execute or take a terminal from here. So if you have a terminal access, you have the whole access to whole computer. So okay, let's try to take a shell from this terminal itself. I will quit, and then I will start GDB again. Now I will load the payload, and without any breakpoint, we are trying to pass it to the program, and we can see we got a shell. Yeah, we can execute all these commands. So we eventually got a shell, but that is inside GDB only. So let's try to run it outside GDB. Vulnerable and cat demo5 is showing a segmentation fault. It is because the address layout of the GDB might not be as same as when we run outside GDB. So it is harder to gain a shell like this in this method. So we use another method. So before telling that method, I would like to show you the stack. And again, we will set a breakpoint at main, and then we will run programs in cat demo5, and then disassemble one func. Then we will take this address, enter a breakpoint. Since it is an address, we will put star, enter a breakpoint, and now we will continue. Yeah, we have hit a breakpoint. So now let's check the stack by /100x and $ESP minus 268 because that's offset. And now if you see the value of EAX, it is currently holding this address, and this address points to the top of the knobs. So what we can do is we can just write a program, or just pass the address of or we can just jump to EAX, and the EAX contains the address of this knobs. So it will then eventually go to the shellcode. So the idea is from EIP, instead of this address, we will write like jump EAX. We will write a assembly code jump EAX, and it will jump to this address. And EAX has the knobs, and it will come to this knobs, and then it will pass on the instruction as it is a knob, and it will eventually hit the shellcode. So let's quit that, and okay, I have already prepared that exploit also, but before that, I needed GDB once more. Okay. Seem to hit some error. Oh, okay, that was a mistake from my side. Sorry, I will do it again. I have to disassemble one from. Yeah, seems familiar. Start and then copy, paste, and then we will continue the execution. So all these instructions like jump, push, move, subtract, everything is coming from a library called lib32-libc. It is coming from here. So what we can do is there are addresses of these assembly codes in this. So I will take the address of jump EAX and then write it as write it into EIP. So first, okay. First, I will copy this address. This is the base address where the program is loaded. Make sure that is copied. Exit GDB. I will clear the screen, and then I will I think it's the same, right? Oh. Okay. Here it is. So now we got the base address of that library. Now we have to find the offset, that is the address of jump EAX in that file. Now we will save this, and since okay, I cleared it, we'll try to copy /lib 32. Okay, lib c, c. Yeah, I forgot. I have to use GDB again. Sorry. set a breakpoint at main. And then I will run it. Yeah, we got this. See here. Share that address. So we will copy that file that we saw to this directory, and yeah, that file is here. So now we will use a tool called Ropper. It is used to search the instruction inside this file. So first we will type Ropper, and then we will type file, and we will type libc, and the Ropper is trying to load that file. It will take some time. This is just a first loading. Yeah, this takes a lot of time. Hope the shell doesn't die. Oh, it's going faster than I expected. 13, 14. It's taking a lot of time. Bear with me for a few more minutes. This session will be over soon. So we are at the final stage of creating an exploit which will run outside GDB also. I hope everything up to this point was pretty clear. Shane, was there any question from the audience?
No, Shibin.
which is 88, 89, 90.
Five, 7, 8, 9.
The file is loaded. Now we will search and we will take a depth of 1. This is to specify how deep the search has to go, and then we'll type jump EAX, and we got the address. We will copy that. We waited that long for that small address. Now we will open that exploit, and it was here already. No, that's not the same. So now we will have to, this is the base address and this is the offset. So we will have to add these two to get the actual value of jump EAX. So we will take a hex calculator. And then we will type a base address F7 FD D0000. Then we will have to add the address of jump EAX with the base address. We got a value. Copy that. Then we'll paste it here. And then as usual we will be entering it, but in reverse order. Like I said, it is using little Indian. So /x d3 /x 91 /x de /x did I miss something? 9 1 2 4 5 6. Okay. Yes, there's an extra 0 here. Let's just see how it is. So D3, let's see 3 6 1 /x FD /x F7. Now let's see if that works. And we will write to final exploit. Now gas broadcast. I hope this works. And yeah. Exploit. Now there seems to be some error. So we can fix that. This is correct, right? So /tp/ we will double main, and then we will run using demo file. the base address, right? F7 FP E0 00. Okay, but still it's another. Let's try this address. 7 EAB 000. We got that value. Now we will go back to our exploit. We will change it here. Slash x 83 slash x 41 slash x p0 slash x f7. So if this works, we will write it on final exploit again. And we got a shell without using GDB. So that concludes our session today. Any doubts?
Shibin, there's a question from Anurag. Can you please describe how to compile the C program in 64-bit system to check this exploit?
Okay, actually, there's an extension. Okay. Can I switch off my sharing? I will share it in a moment. It was compiling C program. That's it.
Shibin, your screen is not visible right now.
Yeah, I turned it off.
Okay.
Can you see my screen now?
Yeah.
Yeah.
Perfect.
So this is the command that we use.
Shibin, can you zoom it?
Yeah. Okay.
Yeah. Cool.
Better.
Yeah.
So we have to compile the vulnerable.c program, and we make it 32-bit compatible, and then we will turn off the stack protector, which Anil told was a prevention method for buffer overflow, and then we will disable the execution stack, and this is for stack and protection, and then for the output we will be writing it on vulnerable. I hope that clears the doubt. See, if you are running on a 32-bit machine itself, you don't need to add this This is to make it 32-bit compatible. I am running on a 64-bit machine, so I need to use this to compile. These are all to disable all the protections from executing a buffer overflow.
Okay, Shibin,
Any
there's
other
another
doubts?
question. Can we automate the whole process and get an interactive shell somehow?
Can you automate it? I didn't hear you.
The whole process and get an interactive shell.
Sorry, I still didn't hear you.
Okay,
Automate what? Okay,
this whole process, the
automate.
whole exploitation process.
Actually, it is pretty hard. Like while automation, you don't know the address and all, which address you are going to point to. So it might be a bit hard. It might be possible, but it is very hard. That's why we the final exploit that we created acts as it works on all the platforms. You don't have to take GDB and analyze it. It will automatically jump to EAX and then it will execute. It is harder to automate this process, in my opinion. I don't know if it is there somewhere.
Thank you, Shibin.
Any other doubts? So this is how you can contact us. I'm Shibin, and the assembly language session was taken by Shine, and introduction was given by Anil. I think we can wind up this session if there are no questions.
So, all right. So if you don't have any other questions, we can wind up the session. Thank you, Shibin, Shine, and Anil for the session. You guys did a wonderful job. And audience, thanks for your time and the active participation. Hope you found this session useful for you. Please share your feedback via the form available in our Facebook and YouTube channel. See you again in the next chapter meet. Until then, take care and stay safe. Goodbye.
Bye.
Goodbye.
Bye.